Hello everyone, my name is Cheng Siwei and my metric number is ES04492. Look at the components in the figure. There are four stator windings which are connected to form opposite coil groups across the rotor. In the figure, the upper and lower coils are phase A and the left and right coils are phase B. The coil is connected in such a way that when the current passes through the N and S poles, the N and S poles face each other. Each rotor in the picture has 15 teeth, and if the white rotor is in the front and is magnetized to the impole and the permanent magnet, and then the blue rotor is in the back and is magnetized to the ice pole.
Hello everyone, my name is Zoltian Chen and my metric number is 209787. I'm going to introduce the work principle of Hybird step motor. Here's the videos with references.
There are various types of stepper motor. This type is a hybrid motor, which is the most commonly used. We see the motor consists of two end caps and the main body. The shaft sticks out from one end, and the electrical connections are usually found at the opposite end. Inside the motor, we see there are two bearings attached at either end of the shaft. These hold the shaft in place and ensure a smooth rotation. Attached to the shaft, we find the rotor. The rotor and shaft rotate together. The rotor is a permanent magnet, which has two halves known as cups. One cup is the north pole, and the other is the south pole. There are a number of teeth carved into the outer surface of each cup. The teeth of the two cups do not align. They are offset from each other so that the teeth of one cup aligns with the gaps of the other cup. Surrounding the rotor is the stator. The stator remains stationary and does not rotate. This consists of a number of coils of wire which surround the rotor. The coils are not all connected together. In this example, there are 8 coils, which are connected in two groups of 4. The driver will control when electrical current can flow through these coils. This creates an electromagnetic field which causes the rotation. There are teeth surrounding the inner perimeter of the stator also. These are used to enhance the precision of the motor and create magnetic alignment. The rotor has more teeth than the stator. For example, the stator might have 48 teeth, while the rotor has 50 teeth. This difference means not all the teeth will be able to align at the same time. When one set of coils is energized, the coils will form electromagnetic fields with north and south polarities. The rotor is a permanent magnet, and this will interact with the stator's electromagnetic field, causing the rotor to turn. The coils will turn on and off, and the polarity of a coil's electromagnetic field will reverse each time it turns on. This causes the rotor to rotate because the stator coils will attract and repel the rotor cup's magnetic field. We know that magnets will interact. The opposite ends will attract while the alike ends repel. When current flows through a wire, it creates an electromagnetic field. If we wrap the wire into a coil, it creates a larger, stronger electromagnetic field with a north and south pole. We reverse the polarity by changing the direction of current. We can turn the magnetic field of the coil on and off by simply allowing or stopping the flow of current. But the magnetic field of a permanent magnet is always on. If we place a magnet centrally and allow it to rotate freely, we can use other magnets to rotate this. We can also place electromagnets around this and control the rotation by controlling the current flowing through each coil. The more coils we use, the more precise the rotation. A simple way to control the coils is with an H-bridge. If we imagine the motor has 2 coils, and each coil is connected to 4 switches, if we close switches 1 and 4, coil 1 polarizes, attracting the rotor. Then we close switches 5 and 8, causing the rotor to turn because of the attraction and repulsion of the magnetic fields. Then we close switches 2 and 3. The polarity has now reversed and the rotor turns. Then we close switches 6 and 7 to rotate the rotor again. Then we close switches 1 and 4 to complete the rotation. The switch sequence continues, causing the rotor to turn. Reversing the sequence reverses the direction of rotation. Changing the frequency of switching controls the speed. The switches are electronic instead of manual, allowing us to program them to turn on and off with precise timing. We'll look in more detail about controls later on in this video. We have also covered how transistors work previously. These are a type of electronic switches. I'll leave a link in the video description down below for you.
My name is Zhang Ludan. My matric number is ES04501. Let me introduce the application. Hybrid stepper motors indeed play a crucial role in enabling precise motion control and efficient operation in a wide range of systems and equipment. Their ability to combine the strengths of permanent magnet and variable reluctance stepper motors make them an ideal choice for demanding applications that require high precision, torque, and reliability. It can use this following three ways. In automotive systems, such as electronic throttle control, active suspension systems, and automotive instruments cluster for precise control and reliability. In medical devices, like robotics, surgery systems, imaging equipment, and laboratory automation systems, where precise control and reliability are critical. In laboratory automation, such as liquid handling, simple processing, and robotic assays, where precise movement and control are necessary.
Okay, here is the advantages, and the first is high torque. Hybrid speed motors provide higher torque than PM step motors, especially at lower speeds. And the second is efficiency. They are more efficient in converting electrical power into mechanical motion compared to other types of stepper motors. And the third is low vibration and noise. The design helps in reducing vibration and noise, leading to smoother operation. And the last is high precision and resolution. Due to their fine step angles, hybrid stepper motors offer high precision and resolution, making them ideal for applications requiring detailed control.
So here is the main disadvantage of hybrid stepper motors. First is complex structure and relatively high manufacturing cost. Since the hybrid stepper motor uses a special structure that combines permanent magnets and electromagnetic coils, its production cost is relatively high. Second, the rotor interior is large, which may affect the response speed of the motor when running at high speed. Since hybrid stepper motors usually use large rotors, their interior is large, which may affect the response speed of the motor when running at a high speed. The third, a lot of heat may be generated during operation, and good heat dissipation measuring are required. Since the hybrid stepper motor needs to use permanent magnets and electromagnetic coils at the same time when working, it will generate a lot of heat, and effective heat dissipation measures need to be taken to ensure its normal operation.